See, in the previous class, we were discussing about what electric potential due to a point charge. Due to a point charge, what is the formula? V is equal to 1 by 4 pi epsilon 0 into Q by R square, Q by R. This is due to the point charge. Now, if there is a dipole, the formula is 1 by 4 pi epsilon 0. What is that of that? Anyone? What is the formula for dipole? V is equal to 1 by 4 pi epsilon 0 to P by R square, right? P or P cos theta divided by R square. Are you referring? This chapter is very dry. You have to do it, okay? Are you there? Yes?
Yes, sir.
Yeah, Moksha, Ismail.
Yes, sir.
Okay. So what is the next formula? That is potential due to a that is electric potential due to a system of charges. What is the formula? V is equal to V1 plus V2 plus dash dash Vn. Okay. So this is the formula. Now next one, we have equipotential surfaces. What do you mean by equipotential surfaces? What is equipotential surfaces? Can anyone say? What is equipotential surfaces?
Where
Yes. Equipotential surfaces. Surfaces with constant potential throughout. Okay. Surfaces with constant potential throughout are known as equipotential surfaces. Okay.
yes,
Known as equipotential surfaces. What is the next one? We found out the potential energy, right? Or relation between V and E. So E is equal to V by D. Okay. Relation between electric potential and the electric field. E is equal to what? E is equal to V by D. What is the next formula? Potential energy of the system of charges. Okay. So potential energy of the system of charges is what? U is equal to what? 1 by 4 pi epsilon 0 into Q1, Q2 by R12. If it is two, if there are two charges. If there are three charges, U is equal to what? 1 by 4 pi epsilon 0 into, we have the formula Q1, Q2 by R12 plus Q2, Q3 divided by R23 plus Q1, Q3 by R13. Is that clear? So we have three formulas. U is equal to 1 by 4 pi epsilon 0, Q1, Q2 by R12, Q2, Q3 by R23, and Q1, Q3 by R13. So these are the three formulas for potential energy formulas. Now these are not under the influence of electric field, external field. Means they are only now without any external field. Now we are going to place the charges in the presence of external field, then we will derive the derivations for that. Okay. Clear? So now, is this clear, all of you? Until here. Is it clear? Yes. Moksha and Ashas.
Yes, sir.
Okay.
yes, sir.
Okay. Then I'm going ahead with the next derivation. So here, charge in an external field. Okay. So potential energy of a charge in an external field. So potential energy of a charge in external field. Suppose you're going to place a charge in the external field like this. This is the external field, and you're going to place a charge here, plus Q. Okay, so then what happens when you place a charge in an external field? The potential energy is how much? P is equal to V have W is equal to V have VQ. It's a simple formula. It makes some displacement. This charge accelerates. This charge will accelerate when you apply. What he's saying is, if electron is accelerated by a potential difference of 1 volt. Now suppose there are two plates. Example, positive plate and negative plate. This is the electric field. Example. This is the electric field. Positive plate to negative plate. Done? Okay, we will see that calculus method tomorrow. Okay. Only that is remaining, and relative velocity is deleted, right?
Yes.
So tomorrow we can finish and we can start plane. Okay. Now, what happens because of this, the charge is made and accelerated. So the potential, there is a potential difference. This is the difference is here delta V. And the charge is made to accelerate how much? The charge is accelerated by a distance, but it is making an acceleration. So what do we say here? W is equal to if electron is accelerated, if electron is accelerated by a potential difference of 1 volt, by a potential difference of 1 volt, then that is then we say 1 volt gain of energy, then it is known as 1 volt. Okay, so what happens here? 1 volt is equal to 1 or 1 joule. 1 joule is equal to 1 volt into 1 coulomb. We are writing in there. So therefore, here we write 1 volt is equal to how much? 1 electron volt. 1 electron volt is equal to 1.602 into 10 to the power of minus 19 volts. This is the value of 1 electron volt. And we have 1 kilovolt, 1 mega, 1 giga, and 1 tera. Okay. 1 kilo, 1 keV. That is equal to what? That is 1.6 into 10 to the power of minus 9. Okay, that we are not going to calculate. We have these values: 1 keV, 1 MeV, 1 GeV, and 1 TeV. So A for kilo, M for mega, G for giga, and T for tera. So when I write like this, 1 kilo means 10 to the power of 3 electron volt. 1 mega means 10 to the power of 6 electron volt. 1 giga means 10 to the power of 9 electron volt. 1 tera is 10 to the power of 12 electron volt. Is that clear? Is it clear? So when the electron accelerates and when you apply a potential difference of 1 volt, then the energy here, then that is known as 1 electron volt. So if an electron is accelerated by a potential difference of 1 volt, then it is known as 1 electron volt, or 1 electron, we can write 1 electron volt. Clear? Is that clear, all of you? No one is replying. If you want to convert into joules, how will we do? So 1 electron volt is equal to 10 to the power of minus 19 joules. Sorry, not volts. 1.6 into 10 to the power of minus 19 joules. Clear? Can I go to the next one? Can I go to the next one?
Yes, sir.
Yeah. So potential energy of, next one is potential energy of a system of 2 charges in an external field. Of a system of charges in external field. So here what happens? We are going to place a, suppose this is the electric field. Now there are 2 charges here, like one is Q1 and the other one is Q2. We are going to place 2 charges in the external field, capital E. Then we have to find out what is the total energy. So how much energy is required to bring a charge Q1 from infinity? I'm going to bring a charge from infinity to this point. From infinity to this point, how much energy was required? So that is what W1 is equal to, W is equal to VQ, V1 into Q. V1 into Q1. Okay. Or V into Q1. So what is the formula here? That just leave it like that. V into Q1 of V of, or we can write V of R1 into Q1, because I want to bring it a distance of R1. It's not V into, it is V of R1, because I'm taking a distance of R1 from the origin. Like suppose if you draw a origin, so maybe this is R1 and this is R2. Okay, position vectors. So we're going to move a charge from infinity to this point is how much? W2 is equal to V of R2 into Q2. Now I want to bring now I want to bring Q2 under the influence of Q1. I want to bring Q1 under the influence of Q2 under the influence of Q1. I'm not only bringing in the this charge, I'm not only bringing in the just in the electric field, also bringing close to the under the influence of Q1 also at the same time. So what is that? that is what W is equal to, so W is equal to what? Next formula is the energy W3 we can write here, that is equal to 1 by 4 pi epsilon 0 into Q1 Q2 by R1, Q1 Q2 by R1. So the total work done is equal to how much? Total work done is equal to total work done is U is equal to, we are writing V Q1 into V of R1, Q1 into V of R1 plus Q2 into V of R2 plus 1 by 4 pi epsilon 0 into Q1 Q2 by R1. Okay, this is the formula. Is this clear? Q1, is this clear? Suppose like in only potential energy, if it is there is no external field, we don't write this one. But if there is external field and we are going to bring the charges in the external field, then we have W1, W2 to be added to the actual value. Is it clear?
Yes, sir.
Yeah, please. Please note down this, then we'll go to the next one. If you want, you can write the word work done to bring. See, work done here we can write work done to bring Q1 under the influence of or in an external field, under the Q1 in external field. Q1 in external field. How much it will be? This will be W1. Similarly, work done in bringing Q2 in an external field. Like that you can bring. And this is the same one. Third one is what? Potential energy of two charges. Is this one. Okay. Please copy this first, then we can go to the next one. This is little dry. There is a charge here, minus, this is negative charge and positive charge. So electric field is there here. Now, the distance between the two charges is 2a. So here theta is the angle here. So it will become what? We get a cos theta and a sin theta. So this one and this one, this is minus a cos theta, and this one is plus a cos theta. Okay, so here we have, there are two charges, Q1 is equal to plus Q and Q2 is equal to minus Q. So we have the formula tau is equal to what? P cross E. So we have work done is equal to what? W is integration of tau theta into d theta. From where to where? Suppose when you place a dipole in the presence of electric field, if you place a direct dipole in the place of in the presence of electric field, it starts aligning. Okay, this will align the field and this will align opposite to the direction of the field. So we have theta 0 and we have theta 1. So tau external and theta and d theta. So what is the formula for torque? Torque is equal to P sin theta. From theta 0 to theta 1, P sin theta d theta. Okay, this is what work done by a variable force. This is the formula for work done by a variable force, integral or rotational motion. See, we have for rotational motion, integral tau theta into d theta. This is for rotational motion, because what happens when you place a dipole in the electric field, starts rotating in the direction of the field. So for rotational motion, the formula for work done is integral tau theta d theta. But what is tau theta? That is P sin theta. Now we will write here W is equal to what? P integration of sin is minus cos. Integration of sin is minus cos theta from where to where? Theta 0 to theta 1. Clear? Theta 0 to theta 1. This is the formula. Now it's not mod, but it is a like W is equal to minus PE and cos theta from where to where? Theta 0 to theta 1. So W is equal to what? Minus PE cos theta 1 minus cos theta 0. Cos theta 1 minus cos theta 0. Okay, if you want to remove that minus, it will become what? It will become PE cos theta 0 minus cos theta 1. Cos theta 0 minus cos theta 1. So that's a formula. Now, if theta 0 is pi by 2, example, if theta 0 is pi by 2, what will happen now? W is equal to implies cos 90 is equal to how much? 0. So answer will be PE minus PE cos theta. That's it. minus P cos theta, and theta here and theta 1 equal to theta. In that case, what happens? W is equal to minus P cos theta. Is it clear, all of you? So we can also write W is equal to what? W is equal to minus P dot E. Is that clear? W is equal to minus P dot E. This is the formula. Is it clear, all of you? Once again, see, suppose there is an electric field and you are placing a dipole in it. The dipole means two equal and opposite charges separated by a finite distance. Is said to be a dipole. The distance between the dipole is 2a. Minus q and plus q. Theta is the angle which is making with the dipole is making with the electric field. So q1 is equal to plus q, q2 is equal to minus q, and work done, and here torque is equal to P cross E. Work done by a variable force. Work done by a variable force in rotational motion. This came from rotational motion chapter, not normal one. Rotational motion chapter from grade 11. So just to substitute this value, tau theta d theta, then what is tau? P cross E, P sin theta. Then integration of sin x sin theta is cos minus cos theta. Then this is theta 0 is lower limit, theta 1 is the upper limit. Then what happens? Minus P cos theta 1 minus cos theta 0. Then you remove minus there. Just bring the just interchange the terms. You'll get plus over there. And theta 0 is pi by 2. Cos 90 is 0. So therefore W is equal to P cos theta. Or we can write P dot E. So this is the energy stored. Or we can write U is equal to P dot E minus P dot E. This is for the dipole. Okay. When you place a dipole in the electric field, this much